Hi, welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but still want to be its friend.
I'm Connie, and I'm overwhelmed by a lot of things, but especially the universe, and I also want to be its friend. Thank you for introducing me, Moiya.
You're welcome. It's been my pleasure. And you have been a good friend to the universe. You've been learning more about it every week. I love to see it. Hi, everyone. I'm Dr. Moiya McTier. I am a long-time friend to the universe because I'm an astrophysicist. I'm a folklorist, so I've enjoyed learning the universe in many different ways. Today, I'm just going to admit it. I'm feeling a little off. The changing of the seasons.
Yeah.
The world around us.
The world around us.
Yeah. Personal cycles that I'm going through. I'm having. I would like to have a moment to complain a little bit. And so I think maybe we could have a recurring segment, not every episode, but we'll introduce a segment called A Bone to Pick with the universe.
Yes. You know what? I do have a bone to pick with the universe.
Okay, that's good. Because friends can, have criticisms for each other.
Absolutely,
yes.
Absolutely. Just something you might need to work on and things that we could improve, together. It's all about unity.
Great. Yeah, so what's your bone?
It's hot, and that's not really we're a great temperature. We're in the Goldilocks zone. Is that what we called it?
Yes.
Okay. So the temperature should be, nice and cool. We've had some great temperatures in the past. We have great seasons on this planet. And you know who's part of the universe? The people. The people who have not been taking care of the earth, have not been taking care of themselves or myself because it's hot. And when it's hot, it's humid. And when it's humid, my body doesn't like it because the space and space sometimes don't mix well.
Exactly.
They react to each other in a variety of ways, as I've learned even more ways since I've started this podcast. And sometimes you take certain medications and you overheat because you take them. So friends out there in the universe, take your meds. Yes, please.
Yes.
2, drink water. 3, make sure you check your meds for sun and heat sensitivities as we approach the height of summer. And 4, encourage people to take better care of the universe so that it's not so hot. So that leads me to 5, which is find your local data center and tell them not to do that.
Like when your phone asks the app not to track, you just go ask the data center, please don't data center.
Yeah, please don't data center. Please don't take the drinkable water or raise the temperature.
I like Alexis Nicole's idea of planting native species that are rare and endangered in your area where potentially data centers might be planned for, because then those lands are protected.
Ah, I see. I thought it was going to go the other way where you would plant something invasive like bamboo and then just they can't outrun it.
Well, that was the original suggestion, but then I saw Alexis Nicole, a.k.a. Black Foragers, note about how that is just mean to the environment in a different way.
Fair.
Fair. As would, setting fire to the data centers be dangerous to the environment in a different way. So yeah.
What's your bone, bestie? What bone do you have to pick with the universe?
Like yours, my bone is less with the universe itself and more with the subset of it called us.
The people.
Specifically, the people who come up with terms in science.
We've shared this bone that we pick.
Well, yeah, there's a general bone, but I have a specific bone today. And it came up while I was researching for this episode. This episode is about microwave light, which we haven't announced yet before. But it's about microwave light, and there's a lot of electricity and magnetism that is involved in any episode about light, because that's the electromagnetic force. And I got so frustrated in my prep for this episode over the term electric field. Because I hear the word electric field, I immediately think electron. I immediately think that it's like the quantum field of the electron particle, the fundamental particle. It's not that.
Oh.
It's a field that's generated from any particle with any electric charge. So it's distinct from the electron, but includes the electron. It is distinct from electricity, but it's kind of related. I feel like we should have called this a charge field so that we have the, I don't know, charge magnetic force. We can still call it the electromagnetic force, but the electric field, I cried over this an hour ago.
You're just so passionate.
Although maybe my true bone to pick with the universe is hormonal changes due to body stuff.
Yeah. It all goes hand in hand because everything is space.
And on that note, I wanted to do a whole episode on the microwave part of the electromagnetic spectrum to see, talk about which parts of space are especially touched by the microwave. You chose this as your next region of the spectrum. Do you remember why? Like, do you have any affinity towards microwaves?
Well, I do, because I was a TV dinner kid, okay? I love a microwave for its convenience, and that's where I'm familiar. And so I wanted to, understand literally, I think I get how microwaves work, right? But how does that connect to the larger universe and what the actual electromagnetic field? Because I'm it's light, and that still trips me up. That it's all light. Especially I'm looking at my microwave and it's spinning and there is a light bulb in there and I'm that's not the light. It's
That's
light.
Not the light.
It's light. That trips me up a little bit. So I just want to know more about that. And I'm imagining I'm just revolving in a microwave, just chilling,
Yeah. And a microwave oven and an easy bake oven, both powered by light, but very different types of light. We will talk about microwave ovens later in the episode for sure, bestie.
Thank
Awesome.
you.
I want to start us off, though, by talking about the general characteristics of microwave light. We've talked about ultraviolet light and infrared, correct?
Yeah.
Okay, and so do you remember which of those has shorter wavelengths, ultraviolet or infrared?
Infrared
has shorter wavelengths?
Oh, okay. So it is ultraviolet.
Yes.
Yeah,
yes. Ultraviolet is the more energetic type of radiation, so it has smaller wavelength.
Yes, and I have to think about it this way of the actual optical and how red is longer, right? Is red longer and then blue is, and to violet is shorter. And so that's kind of how I'm trying to remember it, but I just flipped it in my brain earlier.
Okay, that's a good device.
That's going to help me, I think, for going forward.
Yes. And there's always this inverse relationship between the wavelength of a particle of light and its frequency, which is how much energy it has. Well, technically, the frequency is how many times the peak of the wave would pass through a certain spot in a second. So 1 hertz is 1 oscillation per second. So when we talk about microwave light, we are talking about wavelengths between 1 millimeter and 1 meter. So that's a range of 1,000 times difference from 1 millimeter to 1 meter. In terms of frequency, that goes from 300 gigahertz. So gigahertz means billions of hertz. So 300 billion oscillations or peaks through a space to 300 megahertz. Mega means million. And so that's 300 million peaks per second. And so notice that the longer wavelength, the 1 meter, has the lower frequency, the 300 megahertz.
Okay. So and then flip it. It's okay, yes, but I'm catching up.
Some people cut it off at 30 centimeters instead of 1 meter. So the frequency associated with that would be 1 gigahertz or 1 billion hertz, 1 billion oscillations through a space in a second. So that's the range that we're talking about for microwaves. It's lower wavelength than a radio wave, but higher wavelength than infrared light. And that means that you can kind of operate in the space between where those types of light are useful. Unlike ultraviolet radiation, which is really high energy, really low wavelength, it gets scattered or intercepted a lot as it passes through our atmosphere, so it doesn't make it to the ground. Microwave light has longer wavelengths, so it can move further through our atmosphere before getting absorbed by a particle. But it still does get absorbed by the moisture, by the water vapor in our atmosphere. I have an absorption chart for you. I don't think we've talked about emission and absorption lines in much detail before, but I have a graph that is measuring how much microwave light is getting through the atmosphere at different frequencies of light. If there's a big dip in the line, a big dip along the y-axis, that means you're getting much less transmission of this microwave light through the atmosphere. On this chart, you see more of those deep lines. Emission is when the spike goes up. Microwave light is being produced. Absorption is when the spike goes down because the microwave photons are being absorbed by particles. So you see more absorption of microwave light at higher frequencies, so lower wavelengths, the shorter wavelengths of microwave light, because they are going to be absorbed more readily. Mm-hmm. So most of the microwave light gets through our atmosphere, but some of it does get caught up in clouds and in other sources of water vapor. Like optical light and ultraviolet light, the kind of higher frequency types of radiation, microwave light travels by line of sight. So it travels in a straight path. It doesn't curve around the curvature of the Earth. It doesn't diffract around hills or buildings. So it's really only useful for short distance communication here on Earth, something like less than 50 miles. Otherwise, the curvature of the Earth starts to take the light wave, the light beam, away from the receiver. When we talk about radio waves, we're going to get into their kind of weird properties where they will travel along with the curvature of the Earth, even though they're light waves that travel in a straight path. So yeah, it's going to be a fun time talking about radio waves. But these microwaves are simpler. They're just traveling in a straight line. For their discovery, we have to go back to the discovery of electromagnetism in general, because we talked about infrared and ultraviolet light and how they were discovered when people split sunlight up through a prism and then measured the temperature right outside the rainbow on both ends. That was in the early 1800s. We didn't know that it was light at the time, those other invisible types of radiation. We didn't know that light was electromagnetism at the time. And so it took until the 1860s for scientists to really start to understand the nature of light. In 1865, James Clerk Maxwell, who's a Scottish scientist, he published an article called A Dynamical Theory of the Electromagnetic Field, where he combined electricity and magnetism, these two different fields that people had been studying more separately, into one force.
The ultimate mashup.
Get the Glee kids singing electromagnetism right now.
Yeah.
So he published the rules that govern the relationship between electricity and magnetism. And these rules became known as Maxwell's laws or Maxwell's equations. And there are something like 4 or 5 of them. And they predicted the wave propagation nature, like the wave nature of electromagnetism, of the electromagnetic energy. His idea of electromagnetism was proven and demonstrated a couple decades later in 1888 by Heinrich Hertz, a German scientist, and that's who gives us the unit of the Hertz. He was definitely an engineer of some sort because he's making his own electricity machines. He's a physicist. He's working with optics. He generates radio waves for the first time. Like intentionally. He generates radio waves intentionally for the first time using a spark gap transmitter where you use electricity to create a spark going across a space. And that does produce radio waves because it excites electrons in the space. When those electrons go back down to their lower energy levels, they release photons. This is why, for example, you can't drive cars with regular spark plugs when you're in the National Radio Quiet Zone, because those spark plugs produce radio waves that would then be picked up by the telescopes. There's so much we can talk about in the radio episode. I'm so excited.
Oh my, yeah, because I don't know what that no-go zone is.
Yes, we're really going to have a good time with that. Okay.
Bestie, I just need you to know real quick that I looked up Heinrich Hertz, and his hair is way too tame for someone who worked with electricity. The pictures that they're showing, he has the nicest haircut. Like, his hair is just coiffed, is just gelled down. And for someone who worked with this much electricity, I really wanted to see a picture of him just like Einstein, like with just hair all over the place. Because I can't imagine coming out of it without some kind of electrical damage.
Yeah, a lot of those pioneering electricity scientists would zap themselves a lot. But maybe he used a lot of gel. Maybe you're right. It's like slicked back.
Yeah.
Yeah. So he generates the first radio waves, and then people start using other types of spark generators to produce light waves with smaller and smaller wavelengths, eventually going down from the radio into the microwave. And the first person to generate microwaves at the millimeter level is Jagadish Bose, who in 1894 starts getting into light and optics. Before, he's worked with like plants and math things. Like he's truly a very multifaceted, scholarly person. He generates 5 millimeter waves of light with this metal ball that produces sparks off of it when you pass electricity through. And others then start to follow suit. So now we have this whole group of people who can generate microwave light. And then they can start seeing what they can do with microwave light. The way that they produce it is, well, there are a few different mechanisms here on Earth, but the most common of them have to do with vacuum tubes. So you create a vacuum by pumping out as much air and stuff as you can from a space to create an area of minimum pressure. And within those vacuum tubes, you can then push the electrons. If you give them a particular amount of energy, then you can produce a microwave photon. There are different versions of these vacuum tubes. I'm going to talk later in the episode about magnetrons or klystrons, and these are just slightly different mechanisms to use a vacuum tube where you're using electricity and magnetism to accelerate particles and give them energy, and that produces microwave light. So that's here how we generate them in labs on Earth, but we can also have natural sources of microwaves out in space, of course. Stars produce microwaves. There are no stars that peak in their energy output in the microwave because stars are hotter than that.
Right.
Have we talked about black body radiation before?
I don't think so.
Okay. There is a law in thermodynamics and thermal equilibrium. Okay.
It's in there. I know it is.
There is a law called Wien's law, and it basically says that the temperature of an object will determine the peak wavelength of emission for that object. If that object were emitting all of its heat, like radiating away all of its heat.
Okay.
And the temperature and the peak wavelength are inversely proportional. So a lower temperature object, like an M-type star, is going to peak at a higher wavelength in the infrared than a hotter star, like an O-type star, which is going to peak in a shorter wavelength, more like the ultraviolet. So Wien's law says that if you have a hotter object, it's going to emit most of its energy in a low wavelength region of the electromagnetic spectrum. If you carry that past the temperatures of the coolest stars, to us, for example, us humans, we emit most of our energy in the infrared.
Okay. Yeah.
If you have even cooler objects, things that are closer to 0 Kelvin, then they will emit in the microwave. So that's when we're talking about the cosmic microwave background, which has an average temperature around 3 Kelvin. So really, really cold. And it's really only those objects that are going to peak in the microwave. But technically, everything that has heat is emitting a little bit of microwaves all the time.
Right.
But 90% of the microwave photons in the universe are provided by the cosmic microwave background. There are also objects in space and here on Earth called masers. This stands for microwave amplification by stimulated emission of radiation. So it's the microwave version of a laser, which is light amplification by stimulated emission of radiation.
Okay.
And we can do this here on Earth, or this can happen naturally out in space. They're called cosmic or astrophysical masers. And the idea here, remember before I talked about how photons are emitted when electrons jump from a high to lower energy level. The idea behind a maser is that you have some external source of energy that's pumping that energy into a system. And it creates what's called a population inversion, where there are more particles in the space that have electrons in an energized state than in a low energy state. And when that happens, as the external source is continuously pumping energy into the system, it's almost like the particles are overwhelmed and they have to do extra work to get those electrons down to the lower energy state. So they start releasing 2 photons at a time instead of 1 photon. And that's the stimulated emission, because spontaneous emission is when the electron is just doing what it naturally does. It goes down to the energy level, releases 1 photon. Now it's stimulated. So it's like, no, get all these photons off of me.
Yeah, we gotta work faster. Twice as hard. Yeah.
Yes.
Okay.
Yes. And so then it starts producing extra light in the microwave range, because that's just how the energy is pumped into the system. The maser itself is not the external energy source. The external energy source could be a star or a black hole jet or something, but the maser is not that. The maser is the emitting region that we're seeing shine brighter in the microwave. And that's typically going to be a molecular cloud of some sort. So clouds of hydroxyl, which is hydrogen and oxygen atom together. Water, H2O, methanol, which is like a carbon and hydrogen chain, or silicon dioxide, so silicon with 2 oxygens on it. And if you have clouds that are made up of mostly those types of molecules, I think they are extra susceptible because of the makeup of their electron clouds. They are extra susceptible to these population inversions and becoming masers.
Oh. So all like at the atmosphere level? When you say like talk about clouds, so I'm thinking about like Earth's atmosphere, like
molecular clouds, clouds out in space. Yeah,
those clouds. Yeah.
Yes.
Because you said microwave comes in and it gets absorbed by the cloud. So
I did.
And water. So
yes, you're paying attention.
I'm
but
trying.
No, this is a different type of cloud altogether. Lots of microwave cloud interactions going
apparently
on at different scales. Yeah. Hey there, friends. It's me, Dr. Moiya. Connie went out on the office balcony to look at some clouds, so I have a couple minutes to share some messages with you. The first is a merch update. May came and went. I'm sorry, but we wanted to make sure we found the right artist to work with, and now we have. So we have a date and a final list of items I'm so excited to share with you. We have a couple t-shirt options, a mug with all of the muses from my upcoming book, Mothers of Invention, on it. We have a cozy knitted blanket, a genuine silk scarf, perfect for all my natural beauties out there. We have our Constellations Oracle deck, written by me, yours truly, and illustrated by an artist that Connie knows. And of course, our lunar calendar. All of that is coming your way, available for pre-orders on June 29th. So that's when pre-orders are going to open, and I'm warning you now because we're going to be talking about it a lot in the next month. And I want to apologize in advance, but I'm also kind of not really that sorry, because all of these merch items are fantastic. I can't wait to get my hands on them, and I can't wait to see them in your hands as well. My next message is for all of the patrons who support the show financially every single month. We're an independent podcast, so we rely on support from listeners like you, and we value your support so, so much. Thank you. I want to give a special shout out to our Sun-like stars, Scott Reynolds, Tom T., Seven Petrichor, Ashley Shambo, Bruce Sedloff, and Kelly Bennell. Thank you. You're perfect, and you have the perfect mass for holding down this pale blue pod stellar system of ours. If you want to join this awesome group of people, you can do that on Patreon. You'd get to hear your name on the show, make it onto the patron star chart, and get research notes for most episodes for $5 a month at patreon.com/palebluepod. That link is down in the episode description, as is a link to our PayPal in case a monthly donation isn't something you're interested in right now. If you donate at our PayPal link, you would become a supernova, a transient object in the pale blue pod sky, and we would appreciate that so much. Of course, if you can't support us financially at all right now, we totally understand. The world is difficult and there are other ways to support the show without spending your hard-earned money. You could rate and review the show on your favorite podcast platform, and you can send a link to a specific episode to a specific person who you think would enjoy it. But no matter what you can do, thank you for listening to the show. Connie and I are so happy to be a part of your week, and that's why we keep coming back. So thank you, and we'll be back next week. My final message is a podcast recommendation. It's another show in the Multitude Collective called This Guy Sucked. This is a history podcast for haters by haters, where you can join historian Dr. Claire Aubin and a new expert every week to pull back the scholarly curtain on some of the world's biggest bummers. From Charlemagne to Carl Schmitt, no dead person is safe, and the show's guests prove that the best part of understanding the past is criticizing it. They recently did an episode about Ramses II, so you should check that out if you, like me, had a copy of that big golden Egyptology book with the red stone on the cover. I know you know what I'm talking about. New episodes come out every Thursday. Get them wherever you listen to your podcasts, and the show is This Guy Sucked. Okay, Connie's come back. She has refreshed her understanding of the different types of clouds in Earth's atmosphere, so we are ready to keep talking about microwave light. So that's how you can form microwaves on Earth and in space. Now I want to talk about how we use microwaves. First on Earth, because I want to get to your microwave ovens.
Yes. I'm like, I don't actually know how they work.
You will at the end of this episode. Mostly. So a microwave oven is a box that can trap radiation. So it's like a Faraday cage. We haven't done an episode on Michael Faraday. Maybe we will. After prepping for this episode, I definitely want to do one on Jagadish Bose, because I think he is such an interesting figure to learn more about. But a Faraday cage traps in electromagnetic radiation, so it can bounce around and, amplify on itself, perhaps. So a microwave oven traps in microwave light. There is the light bulb in there so you can see what's going on, but that light bulb emits in the optical, and that is not the source of the microwave light that's actually heating up the food. Completely separate.
Wild.
Yeah. Yeah. These microwaves are typically powered by something called a cavity magnetron, which is one of those types of vacuum tubes. So they generate microwaves at a particular frequency of 2.5 gigahertz, or a particular wavelength of about 12 centimeters. I think it's a pretty common belief, and I'm pretty sure even I have said this before on the pod, and I'm so sorry, that that frequency is like a resonant frequency of water that is particularly chosen to excite water molecules. That's not the case. It's actually a much simpler mechanism. It's called dielectric heating. This works for molecules that have a dipole. So they have a positive charge on one side of the molecule and a negative charge on the other side of the molecule. Water is famously a dipole molecule. And there are other dipole molecules in our food. The sugars and fats can be dipole molecules, but this wavelength of light is good at vibrating those dipole molecules.
Okay.
The light waves produce a changing magnetic field, and because the magnetic field is moving, the charged particles or any dipole particles are going to be moving along with it. So as the field goes back and forth, the molecules will spin and rotate, and they'll generate basically heat through friction, and that heats up the food, especially on the outside. And then the inside parts are heated through conduction. So there's another common misbelief that a microwave cooks things from the inside out. No, from the outside, and then the heat is carried in by conduction.
You know what? That actually makes sense, because when you put things in the microwave and everything in the middle does not end up microwaved. And it does track that everything I put in there does kind of, I know you mean like in and of little steak bite or whatever, like that's the last thing I microwaved, and was like unsatisfied with how like deeply it did it. But like, say you have that piece of steak and it only does the outside of that, but also the whole plate.
The light waves, they have peaks and troughs, so you have to be careful about the distances of things. And that's why it spins, so that it's more likely that all parts of the food will get covered by a peak of the wave. So it's pretty complicated, actually.
Yeah.
But I think much less complicated than choosing a special harmonic frequency of water molecules specifically, because you don't want just the waterier foods to heat up, although that is typically how it goes, because water is very effectively, influenced by this method.
Yeah, when things are dry, if you're like reheating rice or something, I usually add more water to it. And now that I understand that, it's like, the water is it's doing the work.
The water is the workhorse, but there are also, there's a work donkey made of sugars and there's a work mule made of fats that's doing some of the work as well.
Yeah, gotcha.
Yeah. So that's microwave ovens. There's another use for microwave light that we've touched on briefly before in the Ancient Aliens episode, actually, and it's wireless power transfer.
I saw when you said earlier that it's 2.45 gigahertz for the microwave heating. That is also one of the frequencies for Wi-Fi for lower energy devices. And so, I just know that because sometimes it's like, it didn't work on like whatever the 5 gigahertz is. So sometimes it's like, you might have to look for your lower 2.4 gigahertz. And so I was like, that's a number that's familiar because of Wi-Fi.
Very similar. I mean, both are about using the fact that photons can carry energy over relatively empty space to, transport energy from point A to point B. Because some types of light have shorter wavelengths and some have longer wavelengths, that means some types of light are better for long-range communication or sending energy over long ranges than others. Very short wavelength light, like ultraviolet or X-ray, that's going to get scattered so quickly because the wavelengths are really short and it's not going to take long for it to hit something. The really long wavelengths like radio waves, they can go far and they might even go around objects, but because the wavelengths themselves are larger, it is harder to direct a beam. It's harder to create a narrow, collimated, strong beam of light. So
it's like flimsy.
You're wiggling your hand.
It's giving flimsy. It's like not, instead of like a strong sword, it's like a pool noodle. That might not be the right analogy, but
I think it's more like it is a really broad sword, and so it's hard to wield precisely.
There it is. Okay.
And so there's this balancing act. You want a big enough sword to cause damage on your opponent, but it needs to be small enough that you can wield it properly. And so it turns out that for this wireless power transfer, microwaves are the sweet spot where they're big enough wavelengths that they're going to make it through most stuff, but small enough wavelengths that you can really direct the light beams. And this is, why some people think that you could generate power and then transport it to alien civilizations by beaming out microwave light. We have created devices called rectennas that can receive the... I know. That can...
What? Wait, no. I was ready to move on. I really was ready to move on, but I looked at the agenda and it said rectenna is just a tear. No. The rectenna can receive microwave light and convert it into electricity. Actually, it can do that with any type of light, but it's most efficient, about 95% efficient with microwave light. Thank you, rectenna. Is that why the conspiracy theorists do the tinfoil hat and don't like microwaves? Are those things connected?
Maybe. There are a lot of different camps that I came across in my prep. People who think microwaves are, like as they pass through you, they cause cancer. People think that with lots of different types of radiation. But I think this idea of hats to keep out any sort of waves probably has to do with the remote control use of microwaves, where kind of along similar lines, they're the right type of wavelength to go far, but be easy to use, and they're not dangerous like ultraviolet or X-ray radiation would be. So they're used in a lot of remote controls, like a remote control for your TV or your radio. Yeah. They're used in remote sensing and radar. So it's like two sides of the same coin. Surveillance, weather tracking. Basically, if you want a beam of light to make it from one point of Earth to another relatively nearby, you're going to use microwave lights.
Gotcha.
We can also use them for medical treatments. The camp says that they cause medical issues, and I don't know enough about the body to know that that's not like 100% the case,
Right, yeah.
But for the most part, it should be fine. It's not an ionizing type of radiation. It's not high enough energy to actually interfere with the atomic nature of your body, but it can be used to target parts of your body. There are cancer treatments that use microwave light to target specific areas and excite the molecules in them to generate heat, to stimulate healing processes, or I don't know if you can overheat and kill a tumor, but like they do use this in some cancer treatments. They use this a lot in diagnosis because microwaves are good at the remote sensing. They can use it to kind of scan your body in a different way from using X-rays to scan your body. Like it's going to show the softer stuff inside you.
True.
There are so many other uses along those similar lines that rely on remote sensing or remote control or transferring energy.
Right.
In space or in astronomy, we mostly are using microwaves to study the cosmic microwave background. I did a whole episode on the CMB. It was episode 136. So go check that out if you want more details about this. But I will say, because Connie, you weren't there, do you know anything about the cosmic microwave background?
You've mentioned it a little bit to me. I think it's like remnants of the Big Bang. Okay. And it's the remnants, and that is helping me to remember that they're cooler. And I don't know if that has anything actually to do with it, but it's been left out for a really long time.
It's like the coals of the fire. Like they're burning down.
They're still burning back in the background from long ago.
I love that. So it's not necessarily a signature of the Big Bang itself, but it is as close to the Big Bang as we can get through visual or light-based observations. Because immediately after the Big Bang, the universe was opaque. It was too hot and too energetic and cramped. And so the photons, it took time for the photons themselves to form. But once they formed, they were trapped by all of the free-floating particles in space, especially the electrons. It took 300,000 years for those electrons to bind on to atomic nuclei and become neutral atoms and leave space free for the photons to escape and reach us. So when we see the cosmic microwave background, we are seeing photons from that moment of recombination. We're seeing the distribution of particles at that precise moment. And at that precise moment, the radiation that was released was most likely infrared radiation. Like maybe a little closer to optical, but I think we've placed it in the infrared. And as the universe expanded and all of the light that was traveling through the universe got stretched, got redshifted, the light shifted from being in the infrared to being in the microwave. And eventually, many billions of years from now, it will not be the cosmic microwave background, but the cosmic radio background, because the light waves will get stretched even more.
Wow. You'll level up someday.
Like a Pokemon evolution.
Or is it down?
It's all in the eye of the beholder, I guess. There's no orientation in space.
Yeah.
So the cosmic microwave background was discovered in the 60s. And I like this story because it shows how sometimes astronomers or scientists in general are so wrong with what we think something is, but that can lead to the most beautiful discoveries. So in the 1960s, there were two scientists at Bell Labs in New Jersey who were using an old telescope called the Holmdel Horn Antenna. It kind of just looks like a big cornucopia, a big metal cornucopia.
Okay.
The two scientists were named Robert Wilson and Arno Penzias, which is such a fun name. Mm-hmm. And they were trying to study masers in the intergalactic medium, the space between galaxies. But as they were taking their observations, they noticed that there was a persistent and annoying low-level background of microwave radiation. And they tried to remove it from their signal by figuring out what the source of it was. They turned it to different directions, seeing if it was an earthbound microwave source. They tried turning it towards the galactic center. It wasn't really that. They noticed that there was a bunch of bird poop on the telescope, so they cleaned that off, and the signal remained. So eventually they realized that there is this signal coming from the entire universe all at once, and discovered the cosmic microwave background, which then helped them learn more about the Big Bang and was one of the pieces of evidence for the Big Bang theory, but doesn't tell us directly about the Big Bang itself.
Gotcha. Okay.
So that's 90% of the microwave photons that exist in the universe. The other 10%, they're produced by stars, they're produced by us, and we can use them for cool things like particle accelerator research.
Oh.
Apparently, most of the particle accelerators that have been built on Earth rely on microwave light to actually do the accelerating of the particles. I talked about the cavity magnetron that powers the microwave ovens. There's instead something called a klystron, or a cavity klystron, that powers the particle accelerators, and it's a similar mechanism. It's a vacuum tube. You excite the electrons until they generate enough photons in the microwave for you. But the klystron, as opposed to the magnetron, is able to produce more linear and directed microwave beams, which is exactly what you want when you're trying to accelerate like tiny little particles. So you can direct the beam at the particles. The particles kind of get carried along by the microwave light, and they get trapped in this cavity, this resonant cavity where they cycle around and around and around, picking up speed until they reach the accelerations necessary to do whatever research they're doing. And most of the particle accelerators use microwave light, but the newer, fancier ones use lasers, which are optical light.
Oh. They've leveled up.
Yes.
I imagine the klystron is like much bigger than like my microwave magnetron.
A little.
Just a little bit. Just a little bit. Is it like a big, giant building size, or is it just like a part of... Because I guess I've never really pictured how big an actual particle accelerator is.
The circumference is about 16 to 17 miles.
Wow.
Mm-hmm.
All the way around.
Quite large.
Huh. Yeah.
Quite large. Yeah, a vacuum tube that's 17 miles in circumference.
Wow. That's big.
Yeah, pretty impressive. And part of the reason they wanted to shift from microwave light to lasers with optical light is because those smaller wavelengths allow you to accelerate the particles in a slightly smaller space. That's how we use microwaves to learn about the universe, but we need specific instruments to do a lot of this. I've talked in the CMB episode about the 3 observatories, the 3 missions to really map out the cosmic microwave background. So we have COBE, the Cosmic Background Explorer, which operated from 1989 to 1993, and it was the first full sky CMB map. But it was pretty crappy. It was low res, and we needed an update. So in 2001, we launched WMAP, the Wilkinson Microwave Anisotropy Probe, and that operated until 2010. Yes. Anisotropy, I think, is the vocab word for this week. It just means a small discrepancy. It means a small change from the average field. When we look at the cosmic microwave background, it's areas of slight over and slight under densities. And that deviation from the average density is called an anisotropy because it means like a thing that is not the same as everywhere else.
Okay. That definitely is a new word.
Yeah. Yay. But WMAP, even though it was better than COBE, we could still do better. So in 2009, we launched Planck, and that is also mapping the entire sky, still in operation, mapping the entire sky for the CMB.
Nice.
Outside of those three that are really focused on the cosmic microwave background, we have the South Pole Telescope, which is a collaboration between the National Science Foundation and the U.S. Department of Energy. It's led by researchers out of the University of Chicago, and it is at the South Pole. It's a 10-meter telescope that is using microwave light to study the very early universe. It's trying to find evidence of gravitational waves left over from early on in the universe, like the inflationary period. So they're trying to study how the universe inflated, like in the first second after the Big Bang. We are using the South Pole Telescope to look for the first galaxies that ever formed and the first galaxy clusters that ever formed. It is also mapping the anisotropies in the cosmic microwave background, but it has a very cool honor of being a member of the Event Horizon Telescope Network. So the interferometer, the many telescopes around the world working together to take a picture of event horizons around a black hole. This is one of the telescopes in that network.
Oh, nice.
And then we have the Cosmology Large Angular Scale Surveyor Telescopes, or CLASS telescopes in Chile. It's an array of 4 different telescopes that are all focused on different frequencies in the microwave range. So one is focused on 40 gigahertz, one on 90, one on 150, and the fourth on 220 gigahertz. It is specifically measuring polarization in microwave light. Polarization is basically like the orientation of the light wave's electric and magnetic components compared to the direction of travel. So the light wave is moving forwards ahead of you. But light is electric and magnetic. It has an electric field and a magnetic field component.
Right.
Those two are perpendicular to each other. They are also perpendicular to the motion of direction. So if the light is like moving away from your face, then the electric and magnetic fields are moving like up and down. And then side to side like a snake slithering up and down and a snake slithering side to side. However, imagine it's still those two snakes. You can keep those snakes the same relative to each other, but rotate them so that the snake isn't going like up and down, side to side, but they're both going diagonal.
Okay.
Right? That angle where you rotate them, that's the polarization of the light. And you can use that to your advantage. You can develop filters that will only let a specific polarization of light through. You could... I remember you can use the polarization of the light to understand more about the changing of the magnetic and electric fields because it's going to switch over time. But the CLASS telescopes are specifically looking at that, measuring the change in polarization, which is really measuring the change in like the interactions between electric and magnetic fields.
Wow. Okay. What's interesting is that it also made me think of polarized lenses, like for a camera or for your eyes, where it only lets in... Like it affects what kind of light gets let into either your eyes or to the camera.
Yeah, exactly. Because it's only letting in like 90 to 60 degree polarized light, for example.
Yeah. Huh. Now I'm just thinking of like a giant camera filter on the telescopes that they just like have to like screw on. It's a funny image.
I mean, kind of. Like that is, there's a lot in common between telescopes and cameras. Awesome. Any lingering questions or thoughts about microwave light?
No, I think the microwave is just spinning in my mind, and at some point it'll beep, and when it does, I will let you know.
Yes. And as with all learning dishes, you might have to reheat it a couple times.
Yeah, experiment with times, to make sure that it cooks but doesn't overcook.
Yes, indeed. But I know that I threw a lot at you. I imagine that, much like those molecular clouds with the masers, maybe you're a little stimulated right now.
Definitely.
So I wanted to play a little game to bring us back down, like an electron, to a lower energy level. And this is a game like FMK, like Fuck, Marry, Kill, but microwaves. So instead, it's heating up, zapped, best served cold.
Ooh, okay.
So heating up is like, that's the F. And zapped is the M. And best served cold is the K, because they're like, don't even put it in the microwave. It's not even worth it.
Not worth it. Okay.
Yes. Okay. So I have 3 trios for you. The first, planets, stars, galaxies.
Okay, I am going to heat up stars, because ConStar. I'm going to zap planets, because I live on one. And I'm going to serve galaxies cold.
Oh, why?
Yeah. Stars are definitely a spark, like that's just like a burst, an affair, if you will. Planets provide you stability. They provide you atmosphere if you're on the right one.
You're right. And then does galaxies just process of elimination?
Yeah.
Okay.
And because it's cold.
And galaxies contain more energy than,
well,
either of the others.
Yeah.
Yeah. I would serve stars up cold.
Okay.
And I think I would heat up planets, because we know I'm a planet girly. I love me some Kepler catalog entries.
True.
And I am zapping galaxies, because they have to know big systems thinking. A galaxy is organized. A galaxy is going to plan our vacations. A galaxy is going to keep us spinning in the right direction. It's going to keep our momentum going.
Ooh, that's good. That's good.
Yeah. Okay. Next trio, solid, liquid, gas.
Interesting. Okay. I think I'm going to heat up liquid. I'm going to zap solid and serve gas cold. Gas can be invisible and dangerous. And liquid is slinky, it's sexy, it's
wet,
fluid, it's wet. And solid, I'm a Taurus, so that stability, I just keep coming back to it,
You're right.
Just like solid ground. It's my favorite, one of my favorite things.
I think I might agree with you. I think I might assign it the same.
Wow, okay.
I thought maybe I would zap liquid, but no, you're right. Liquid's a fun time, not a long time.
Yes, like a shower.
Because it's going to evaporate.
Yeah. But it'll come back though. So like there is a returning cycle still.
Yeah, there's some situationships that you just keep returning back to. All right, well, we're in agreement there. Final trio. This trio is like the things that light provides us.
Okay.
The good things light provides us. Rainbows, aurora, or shade.
Ooh.
Which is, I know, technically the absence of light, but it's there.
It's important. It's important. This is tough. This is actually tough, because as I go into a Florida summer, shade is vital. Shade is essential. But also I like pretty things and pretty colors and pretty lights girly. So aurora and rainbows are among my favorite things. But I think I am going to, it's like, I don't want to serve any of them cold. But I think I'm going to heat up aurora, because it's like a once in a lifetime thing that I hope to be able to experience. And I think I'm going to zap rainbows, because I love to see a rainbow and just in life. And I'm going to serve up cold shade. But honestly, that's not necessarily a bad thing. We can find beauty in death.
So right. Yes, we can. Yes, we can. I'm with you. I'm also heating up Aurora because she's so hot.
I mean,
and she's also, like, she comes and goes as she pleases. I feel like you can't hold Aurora down.
You really can't. You really can't. And she's just so bright and flamboyant.
Yes.
And everybody wants a piece of her.
Exactly.
I mean, she kind of like travels as she will, but like the people come to her. A rainbow will come to you. A rainbow will come to you. You can find a rainbow. You can create a rainbow. You can have access to a rainbow at any time, almost. But like an aurora, that is truly a flash in the pan. So, yeah.
So right, bestie. You're so wise. So yes, heating up the aurora. But this is where we deviate because I am zapping shade. I need it. I need to be able to step out of the sun. Apricity is nice. The heat from direct sunlight is nice. But I need the shade to survive.
Yeah.
And for contrast, right? Imagine a world that's all brightness. Like that's...
As a photographer, the shade is important for that as well.
Yes.
Like, one, it does create contrast. Two, you can't take great pictures in just plain bright sunlight, as you and I actually experienced last summer. And so, yeah, I'm with you.
Yeah, indeed. And I am serving rainbows up cold.
Wow.
Because
during Pride?
I know, I'm sorry. It's just... This is process of elimination. I truly cannot live without shade, and I would rather see an aurora than a rainbow. Because if I'm being brutally honest, I've seen a lot of underwhelming rainbows.
You know what? That's fair. Where I can only see a couple of colors, and I'm like, ooh, you're not giving your best today.
And we can't give our best every day.
And we can't,
literally
and that's
impossible.
Fair.
Well,
but, you know,
that's a good note. That's a good lesson that we all should remember. Wow, we really came into this episode
with bones to pick.
With bones to pick, and now we're ending on a, I hope, hopeful note.
Yeah, I think we are.
It's fine. That's just the day it is. Whether you're feeling your best today or not, you're still space.
Pale Blue Pod is hosted by Dr. Moiya McTier and Connie Gibbs. Moiya created the show with the funny and talented Karine Caputo with help from the Multitude Productions team.
Our theme music is by Evan Johnston, our cover art by Shay McMullen, and our audio editing is handled by the superlative Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Instagram or check out our website, palebluepod.com.
I, Moiya, am Go Astro Mo on all socials.
And I'm at ConStar24 on Instagram.
If you want to support our show, join our community at patreon.com/palebluepod or send this episode to your family and friends group chats.
We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
Thanks for listening to Pale Blue Pod. We'll be back next week.